G'day. Today I'm back with a video that I've been working on for a little while now. I'm going to be doing some more destructive testing to see what's the return on investment for increasing the density of your infill in a 3D print. I'll be doing this by measuring the breaking strength of a test piece that has been 3D printed using a grid infill with densities starting at 10% and finishing at 100%. I'll then compare the strength of the test piece against the print time and the amount of material used to try and come up with some sort of chart or graph showing what's the return on investment. And of course, to carry out this test, I'll be using the load measuring system that I built using an Arduino in one of my previous videos. If you want to check out that video, I'll put a link in the description. So here's my test rig. It's a arbor press with a 3D printed punch and die, and I'll be placing a calibrated test piece into the cradle here, then pressing it with the punch until it fails, measuring and recording the amount of force that each piece fails at using my Arduino. Here are the main stars of this video, my calibrated test pieces. Each one is a 10mm by 10mm square and 100mm long, starting at 10% density and finishing at 100% density. These pieces have all been printed in the upright position so that the cross pattern of the infill is actually a cross-section of the long part of the model. I've got a picture of that cross-section here. Here is the 3D prints. They were stopped halfway so that you can see the infill patterns laid out exactly as they are above. It was at this point in my recording that I lost all of my audio. What I was doing here, I measured the mass of each part, then I put it in the press and measured how much force it took to destroy. I repeated the process for each of the 10 test pieces. This is where the results started to get interesting. At first, everything seemed pretty much as expected. The first one breaking at 252 newtons and the second one breaking at 288. Both of those prints having an equal mass, but the print time going up for the 20% infill. The 30% infill though, this one took me by surprise, being weaker by a lot, only 160 newtons. The fourth one at 40% came up again, 427 newtons. The 50% infill increased again, 646 newtons. But then the 60% infill went backwards again and broke at 521 newtons. 70% went up again, 712 newtons. And you can see here they're starting to get pretty hard to break. The 80% infill was also pretty hard to break, and this one let go at 783 newtons. And the 90% infill, this was very hard to break, and this one didn't let go until 979 newtons, and this was by far the strongest out of all of the prints. It also had a faster print time than the 80% infill. I was very surprised when I did the 100% infill that it was only able to resist 600 newtons, which is less than what the 50% infill was capable of resisting. So this really says something about printing at 100%. The extra time and material spent didn't pay off at all. The rest of this video is going to look like a really badly dubbed movie from the 1980s. So I'm just going to cut straight to the end where I say, see you next time, give you a big smile, and then fade out.